Hello everybody, this is Dr. Christopher White and welcome to part 3 of Deformation part 2. Yeah, that's pretty confusing, isn't it? Okay, so we have looked at strike slip and dip slip faults. So what are we moving on to now? Well, now we're going to have a look at some of the features which faults will produce. So we're going to focus on 3 main features. So the first feature is this. This is referred to as fault Brecher. So you can see here we have one side of the fault there and the other side of the fault here. And you can see in the contact between the two along the fault plane, you can see we have a pile of very badly broken up brecciated rock. Well, unsurprisingly, this rock is created by the grinding motion of the two pieces of the two blocks of the fault moving past each other. It's not really a huge shock, is it? And so this material is referred to as fault breccia. So we're going to go into that in detail in a second. The next feature we're going to focus on is something which is referred to as fault striations or scratch marks, or also called fault striae. And these are lines that are gouged into the fault plane by one side of the fault as it moves past the other side. So it will leave these grooves in the opposite side of the fault plane as the blocks move. Now, fault striae are quite important because I'm sure you can work out pretty quickly that they tell us the direction in which the fault is moving. And so they're extremely helpful in trying to work out what our fault is doing and what our fault has done in the past. And the final feature we'll be taking a look at are fault scarps. And you can see a fault scarp running along here. And so a fault scarp is a topographic expression of the movement of a fault below ground. And so once again, we'll go into detail about that in a few slides' time. Alright, so let's start with fault breccia. So, shock horror, when you have two pieces of rock that rub against each other, the contact between the two will be quite abrasive and it will cause the contact to break up and it will produce lots and lots of angular fragments. So, as we can see in both of these images here, we can see we have two faults, one block here, one block here. This is obviously the fault plane here. And in this case, one block here, and obviously this is our fault plane right here. And you can see the fault plane is full of lots and lots of angular pieces of the rock. So you can also see that in these instances, these angular pieces of rock are stuck together by cement. Now, that's because these fault planes are natural pathways along which fluid will move. And when fluid moves along these pathways, it will inevitably start depositing minerals as it moves through the area. And so those minerals that the fluid deposits will eventually go and cement the fault breccia together, producing a solid rock. So fault breccia is a type of rock called a tectonite, which is a subgroup of metamorphic rocks. And so, as you can see, fault breccias are, surprisingly straightforward things. There's not too much, they're not too complicated really. So, that's pretty much it. Now, fault striae or fault striations, on the other hand, are extremely interesting. And there's a few terms that we're going to, discuss, which we all need to try and remember. So when two pieces of rock move past each other, there's obviously going to be a grinding force. Now, a lot of the time it will produce fault breccia, so these pieces of angular rock. However, sometimes when faults move past each other, what will actually end up happening is the two faults will move past each other. All the very, very fine particles, all the very angular pieces of rock in between will essentially break down to form a very fine powder. And as the faults move past each other, that powder will actually end up polishing both sides of the rock. So you'll end up with a surface that looks like this. So this is one side of a fault, and you'll notice just how smooth that side of the fault plane is. And that's because it's been polished by all these very, very fine pieces of rock which have been stuck on the fault plane between the two blocks. And they've essentially acted like sandpaper, smoothing off the rock, creating this wonderful finish. Now, the other thing you'll notice is that you can see that this nice smooth surface has all of these parallel striations running on it, can't you? You can see in this case they're running top to bottom, and in this instance you can see the striations are running left to right. Now these are the result of fault movement. Now this surface, this smooth surface with these striations, is referred to as a slicken side. Okay, wonderful technical term there. So the striations, as we've discussed, are caused by gouging during fault movement, not really a huge shock. So as the two pieces of rock move past each other, obviously, a bit of rock sticking out from one fault block will cut a gouge into the other fault block. That's not really a big surprise, is it really? Now, the other thing that can produce these striations on the fault surface are minerals. So if we have a look at this picture down here, what you'll notice is one side of the fault is this kind of rusty red rock. The other side of the fault is also a rusty red rock. However, you'll notice the striations in this instance are picked out by a rather grubby looking kind of green-yellow mineral. So what's this? Well, these are elongate crystals which have been produced as the fault has grown. So what happens is crystals start growing on the fault plane, and as the fault moves, what happens is the crystals literally start to get stretched out and elongated. Now, they're not physically being stretched out. They're being stretched out because as the fault moves, more and more material gets added to the crystal. And the crystal, which should normally get bigger and bigger and bigger in all directions, starts getting stretched out. It gets bigger and bigger and bigger at its ends. So it starts getting more and more elongate as more and more material gets added as the fault moves. And so what you end up with is a range of crystals all orientated parallel to each other, which will essentially produce a set of fault striae. So these surfaces which have been covered in these elongate crystals are called silicon fibers, and the crystals will grow in the direction of movement. So both the gouges and the crystals will tell us which way the fault is moving. And it's relatively straightforward to work out which direction the fault is moving, especially when it comes to silicon fibers, because all you have to do is stroke the rock. So if you stroke the rock, as your hand goes one way along the fault striae, it will feel smooth. So that's the direction of travel. As your hand goes the other way, it will feel kind of bumpy and slightly rough. That is the opposite direction. So just by stroking the fault plane and the striations, especially if they're silicon fibers, you can begin to work out which direction your fault is moving, which is, once again, is always a helpful thing to know. So the main and most important thing about striations is this. Now, at the moment, we've discussed how we have two types of faults, strike-slip and dip-slip faults. However, when we've discussed these faults, especially the dip-slip fault, we've discussed them in a context of the hanging wall block just drops straight down with dip. But that's not always the case. So let's look at why fault striae are important when it comes to this kind of movement. Okay, just to show you, by the way, here's a beautiful example. So this is the San Andreas fault, and you can quite clearly see the polished surface there, can't you? Very easy to spot. So this is our silicon side, and we can see the surface has these horizontal gouges. So it's telling us, this block of rock is moving essentially in a left or right direction. We don't know which way, but it's moving one way or the other. We can tell based on these, it's obviously not going up or down, it's going left or right. Okay, so why are these striations helpful to us? Well, if you imagine that this is our fault, okay, so this is the hanging wall block here, and this is the footwall block. Now, in the model which we've been discussing earlier, you would expect this hanging wall block to simply just drop straight down with dip. So the dip of this fault plane here is marked out by the blue arrow. So you would expect this hanging wall block to drop straight down, essentially following the path laid out by the blue arrow. However, in a lot of cases, the piece of rock in the hanging wall block does not drop straight down. Yes, it will drop down, but it will also move sideways. There'll be a bit of lateral movement at the same time. This is not uncommon. It's very, very common, in fact. So this is where the fault striations come in. So if we look at the fault plane here, okay, we can look at the fault striations, and the fault striations are going to show us the direction in which the fault block, the hanging wall block, is really moving. So if we were to look at the fault striations on this fault plane here, we would see that this hanging wall block has not dropped straight down, but it has in fact dropped down, and it's moved laterally as well. You can see these dashed lines represent the fault striations. And so this is an extremely helpful tool to us, because obviously it lets us know in reality how our fault is moving. Not, what we predict based on block models, but how the fault is actually acting in the real world. So what this means is our fault has both a dip slip and a strike slip component, doesn't it? Because this hanging wall block is dropping with dip, but it's also moving laterally with strike. And so, if I rub my nose, and so this means that we have, in this case, a normal fault because the hanging wall block has dropped down. That's relatively straightforward. But it's also going to have a strike slip component, which means that it can be classified as either sinistral or dextral. Remember, that means sinistral means left lateral, and dextral means right lateral. So if you think about it, this would be our footwall block, this would be our hanging wall block, okay? And if I move my hand, I can see that as the footwall block has been dropping, it's essentially moved away from me, which means my left hand, which is the footwall, is moving towards me. So my left hand, the footwall, moves towards me, as my right hand, the hanging wall, moves away from me. Okay, because remember, it's coming down the fault and moving this way. Okay, so what I have here is I have a normal fault which is showing left lateral movement. Okay, so think about it. I've got to stop hitting that thing. So think about it. Instead of the piece of rock just dropping straight down, it's dropped down, but it's also moved laterally. And as it's been moving laterally, it's dropped downwards and it's moved away from me. So my right hand moves away from me. My left hand, obviously by comparison, is therefore moving towards me. And so my left hand has moved towards me. There. My right hand has moved away from me. Therefore, this is a normal fault showing left lateral movement. Okay, so that's the power of these fault striations. It's super helpful in really working out what your fault is doing. So here we have a couple of very nice examples of striations. So you can see over here on the top left, we have an example where we have fault striations which are caused by abrasion. So this is the gouging. So you can see we have this nice smoothed surface, and we can see into it we have lots and lots of these very fine striations all running parallel to each other. So that's being caused by essentially physical gouging of one side of the fault onto the other. Down here in the bottom right, we have fault striations caused by crystal growth. And you can see in this instance, the crystals in question are these nice white ones. And you can see the crystals have all grown parallel to each other. They're running approximately left to right. And so this is, as discussed, this is simply because as the fault is moving, the crystals naturally get stretched out due to that fault movement. Now, once again, as I touched on, I'm just going to say this again, the crystals aren't physically being stretched. Okay? Normally when a crystal grows, it will add mass all around itself. However, because the crystal is in a situation where one piece of rock is constantly moving away from another piece of rock, most of the new material gets deposited towards the ends of the crystal. And so that means over time, because more and more material gets deposited at the ends of the crystal, more material gets added, then more material, then more material, then more material, and essentially what you end up with is a long, slender crystal in the end. And you have hundreds of those, thousands of those, millions of those on the fault plane, all orientated parallel to each other, and of course it ends up producing this nice mineralized or stick and fiber surface. So these are our two differences. These are our two different types of fault striation surfaces. So we have a slicken side here and a stick and fiber here. Okay, good. So those were fault striations. I think you'll agree, extremely helpful things. The final feature which is related to faults is called a fault scarp. And once again, this one isn't a particularly difficult concept to grasp. So we can see a fault scarp is the surface expression of the movement of a normal fault. So the offset essentially is produced by one piece of rock, or more accurately, the ground, dropping relative to another piece of rock. So here's our situation. Clearly we have ourselves a normal fault. The hanging wall block here is dropping down relative to the footwall block here. And if that normal fault intersects with the surface of the earth, well, that means as the hanging wall block here drops down, it's going to take the ground, the soil and grass with it, isn't it? So as this block drops down, this area here drops down as well relative to the block up here. So all relatively straightforward. Now, you can spot fault scarps a lot of the time because what you have essentially is you have a very, very steep-sided face. So fault scarps will typically be anywhere between 30 degrees and 90 degrees. However, the vast majority of them will be somewhere in the high number. So they'll be, in the kind of 70, 80, 90 degree field. So if you are in an area where you don't really expect there to be, sudden changes in the topography, and you find there's a sudden drop in the terrain, the first thing you think about is, okay, that could be a fault scarp, because it's a very simple way of producing these stepped drops in the terrain. So if we look at this picture here, we can quite clearly see, in fact in this instance we actually have two fault scarps. We can see we have one fault scarp running along here, around there, and we actually have a smaller fault scarp right there, don't we? You can just make it out. It kind of gets lost a bit by all this sediment down here. So this is our fault scarp right here, and you can see the fault scarp itself is near vertical. Okay. You'll also notice, and this is very, very common, at the bottom of our fault scarp we have a collection of loose material which is being eroded directly off the fault scarp. This is referred to as talus. So all this loose material is talus. So once again, a fault scarp is simply the surface expression of the movement of a normal fault. Okay. So another thing we need to think about is how brittle deformation, so faulting, can actually lead to the formation of ductile features, faults. So you're thinking, all right, here we go. This sounds a bit complicated. So here's our situation. So in this case, we have ourselves a fault. So it's, as you can see, it's a reverse fault because this block is trying to go over the top of this block. And you can see it's relatively low angle. It's less than 45 degrees. So this is going to be a thrust fault. So this block of rock here is going to be thrust over the top of this block here. So when I've written reverse fault there, I'm wrong. It should say thrust fault. So okay, so this block's going to be pushed upwards. So what's going to happen? Well, as this block gets pushed upwards, it's naturally going to push the rock above it up, isn't it? And it's going to cause that rock to kink. And so what you can see here is simply by allowing a little bit of fault movement, allowing this block here to move up just a little, we have caused the terrain here to come up relative to the terrain here. And it's produced a monocline. So as we've produced a ductile feature simply by a little bit of fault movement. Okay, and this is the picture that comes with the textbook, and I've got to be brutally honest, when it really comes down to it, it's a pretty bad picture. I think what the picture is trying to show is there's a fault running this way, and this strata here has been pushed up by the fault, whereas this strata over here in the foreground of the picture represents the material down here, which has not been pushed up by the fault. But I've got to be honest, it's not a great picture. So what happens if our thrust fault breaks the surface? Okay, so it makes it all the way to the surface. Well, in this instance, what's going to happen? Well, this block of rock here is obviously going to be pushed upwards, and eventually, as it gets pushed upwards, it's going to start riding over the top of the footwall block here, isn't it? Yeah? So the rock's going to get pushed up, but it can't just go straight up. Eventually, as it goes up, it's going to start coming over the top of the block here. The problem is if this block doesn't start to behave in a slightly ductile fashion, essentially you're going to have a rigid block. So as this block gets pushed up, imagine this point here, okay? where it's going to start getting pushed up and up and up and up. And as it gets pushed up, you're going to end up with a triangular wedge of empty space, aren't you? Just think about it. As this block goes up and it starts to come over the top here, you're going to end up with empty space between the bottom of the hanging wall block here and the top of the footwall block here. Sorry guys, I have an eyelash or something. So how do we get rid of this? How is it sorted? Well, we're sorted because it ends up forming a fold. So as this block starts to come over the top, it naturally starts to fold and fall onto the top of the footwall block. So we can see as the hanging wall block gets pushed up, it doesn't just keep going upwards infinitely. Eventually, as it keeps getting pushed up, the hanging wall block will naturally start to fold downwards and it will fall onto the top of the footwall block. And it will produce a syncline-anticline pair, and you can see we have the related thrust fault underneath them. Now this is an extremely common structure, very, very common in geology. So we can see it a little bit in this picture here. Once again, not the best example, but we can see the basic principle is that we have these layers of rock each being pushed one over the top of another. So okay, so this is a rather extreme example of this situation. Okay, so in this diagram you can see we have ourselves a layer of rock, and this layer of rock is going to be pushed from the side, so we're going to compress it. So as we squish our layer of rock, well, naturally, first of all, it's going to start failing and it's going to start folding, isn't it? So if we keep compressing our layer of rock, eventually we're going to take our folds, which will be symmetrical, and we're going to start driving them towards being asymmetrical. So you can see here, this fold here is developing an asymmetrical shape. We can see we have a longer low angle limb here and a shorter steeper limb here. So what's going to keep happening? Well, if we keep pushing, this portion over here is eventually going to detach itself from the rest of the block here, isn't it? So as we keep pushing, this portion here is going to fail, and it's going to come over the top of this part of the block here, and we can see that right there. So this portion of the fold has essentially failed. We can see the thrust fault right there now, and we can see that this block is now going to start moving over the top of the footwall block here. And you can see it eventually, if we take this to its extreme, eventually this block is going to keep moving over the top of the footwall block. And so here we can see a real life example of this process. So this is referred to as a sorry, got to double check the term, as a Tipline fold. Okay, and you can see, so our fault itself is marked here in red, and we can see here is our anticline, so representing this portion here, and here is our syncline representing this portion down here, and we have our fault plane marked out here in red. And so we can see this package of rocks here is being pushed over the top of this package of rocks down here. So this is our hanging wall, and this is our footwall. Okay, and once again, this is the result of compressional tectonics. I should point out that each of these is resulting in some kind of fold, and so obviously it must be the result of compressional tectonics. Because think about it, if you're going to fold any kind of material, so once again going back to a piece of paper, if I'm going to fold any kind of material, well, I have to push it to make the fold happen, don't I? If I'm trying to extend it, if I'm trying to stretch it, well, it's not going to fold at all, is it? So folds by their very nature must be compressional features. So here we have another look. So this is a thrust and fold. So here's our thrust coming through here. You can see the fault itself coming through there. You can see the anticline there, and you can see the syncline essentially is right here. Okay, so we actually have several packages of rocks. There's the same layer of rock, you can see it. So here it is in the anticline. Here's the syncline. You can actually see the syncline itself has failed slightly, producing essentially an overriding piece and then essentially another piece that's going over the top of this lower footwall piece here. So there's our fault number 1, and there's the main thrust there. Okay, and so essentially as our hanging wall moves over the top of our footwall, we can see this fold here starts to become more and more accentuated. And essentially this is referred to as a Tipline fold. And once again, this is a very, very common structure where we have thrust folds. So when you have a thrust fold, it's very, very common to find one of these essentially anticline-syncline pairs, or numerous anticline-syncline pairs in fact, at the tip of the thrust fold. Now some of them, like this one, can be very, very small. Some of them can be absolutely massive. So the next question is well, what happens if we're in an environment where we don't just have one thrust in the area? What happens if we have several thrusts in the area? So you can see this right here. So here we have an example where we have 1, 2, 3 thrust faults all intersecting the surface. And we can see each thrust fault is pushing its hanging wall over the footwall. So in this case, this block here is representing the hanging wall. It's coming up and over the footwall block here. In this instance, this block represents the hanging wall, and it's coming up and over this block here, which now represents the footwall. In this instance here, we can see we have this block here coming up, riding over the top of this block. So this is now the hanging wall, and this is the footwall. So you can see the terms hanging wall and footwall become interchangeable once you have multiple faults all interacting with each other. You know, what is a hanging wall for one fault becomes a footwall for another fault. It can become quite complicated. So those are all thrust faults, and obviously once again we have ourselves an anticline related to this thrust fault as it starts to push the rock over the footwall here. So obviously we have formation of what's referred to as cleavage. So cleavage is one of these fabrics produced by the parallel alignment of minerals due to a rock being compressed. Now that's something we're really going to focus on when we talk about metamorphic rocks, so for the time being we're not going to worry too much about that. All you have to know is these metamorphic fabrics, including cleavage, are the result of compressional tectonics. And we also know that the area must be being compressed because of course we have these thrust faults here, also an indicator of compressional tectonics. So here we have an example. So now this, as you can see, is a very, very substantial cliff face. And so what can we see? Well, here it is. We can see the anticline in the cliff face here. So what we're looking at here is we're looking at an anticline like this anticline right here. So we can see in this area here, there is a thrust fault, and it's pushing this block of rock here. So this is the hanging wall over here, over the top of this rock here, which represents the footwall. Now you can see this isn't some, tiny little, 10 meter size fault. This is a 100, meter fault. This is, 100 meter fold. This is a very substantial feature. So you can see these folds produced by fault movement, some of them aren't, some of them are absolutely huge. Now, imagine if we keep this, keep going with this. So imagine we keep pushing this block here until it starts to come over the top of this block. We keep pushing this block here until it goes over the top of both of these blocks. Well, you can see this in this diagram here. So here's our first layer of rock. Here's our first thrust pushing this layer of rock. So this is our hanging wall over this layer here, which is a set of layers, which is our footwall. Then we have another thrust form, and it pushes this layer of rock over the top of this sequence and this sequence. Then we have a third thrust form, and it pushes this sequence of rock over the top of this sequence, and this sequence. Well, okay, so this is what's called a thrust duplex, where you push one sequence of rocks over the top of another layer, over the top of another sequence, over the top of another sequence. And all of this movement, all this movement is produced by thrust faults, pushing one package of rocks over the top of another package of rocks, over the top of another package of rocks. So you're thinking, all right, well, why is this, so interesting? Well, imagine you do this a lot. Imagine you do it hundreds of times, thousands of times maybe. what's that going to produce? Well, just look at the picture here. You take this package of rocks here and you push it over this package of rocks, you've essentially doubled the thickness of the sequence, haven't you? Tripled the sequence thickness, quadrupled the sequence thickness, and so on. Every time you keep pushing another package of rocks over the top of a previous package due to rusting, you've essentially thickened up the sequence. Now, if you do that enough, what are you going to end up with? Well, you're going to end up with a mountain range, aren't you? So thrust duplexing is quite important, because thrust duplexing combined with folding, okay, because remember, when we fold a sequence of rocks, we take a very thin layer of rock and all of a sudden we make it very, very thick, don't we? We've taken a layer of rock here, which is, what, that thick, 2 sheets of paper, and all of a sudden we've turned it into a feature which is, where's my ruler, which is now all of a sudden 10 centimeters thick. So a combination of thrust duplexing, folding, volcanoes and intrusions all combined together will give you a mountain range. So this thrust duplexing is a very, very important process, because if it occurs on a large enough scale, you end up with the Andes, for instance. Okay, so we're going to stop this video here. So once again, pause or stop the video, get up, have a walk around, glass of water, cup of tea, cup of coffee, whatever you fancy, relax for a few minutes, then come back for part 4, which should be pretty fast.